let's start with the motivating example. Actually, the proof is quite general that we would, get it almost right out of this motivating example. And the contents of the main theorem, and then also the proof of the main theorem is not too hard from this motivating example. So the setting is the following. We are playing a game, and this is one player game. So there is only one player, and we will call this player an agent. So here's our agent. The game looks as follows. The agent wakes up and finds an envelope in front. He opens an envelope and he finds a note telling him what type of this is the role-playing situation, like a role-playing game. So there is a type, and we will call this types T. Initially, for this motivating example, consider there are few types, like a set of possible types. We will call this set of possible types omega. And let's just consider for this example a set of 3 possible types. So those are just 3 different possible types that the agent could have in this game. The game itself consists of a mechanism, X, and the mechanism asks the agent, what is your type? But this information on this piece of paper is a private information for the agent. So the agent might choose to be strategic and tell the mechanism that he actually has a different type, not the one that is written on his piece of paper. So we'll assume that all possible types, though, so this set omega is known for everybody. And also we will assume that the mechanism returns an outcome. The outcome, like a decision that the mechanism made. And let's think about the possible outcomes as also a set, contain different number of elements, but for convenience, just let's assume there are also 3 possible outcomes, x1, x2, and x3. So this is going to be t1, t2, and t3. This set of possible outcomes, we are going to call this pi. The game for the agent looks like this. The agent submits the type. The mechanism returns an outcome. The agent computes the value. So the value is what the agent of type I, 1, 2, or 3, gets if he tells the mechanism that he's type J. This is the number of coins that the agent gets by telling that he's type J, getting some outcome, and when in reality he's type I. So he gets this amount of value. So we can think about this value function. So this is going to be called the value function. But for this motivating example, the value function is just a table. So what is this table? The table looks like this. So we have types here and outcomes here. So it's going to be outcome x1, outcome x2, outcome x3. And here we have type 1, type 2, type 3. But you can imagine any dimension of this table. This table could have more types than outcomes, more outcomes than types, not a problem. And every cell in this table contains a number of coins. Let's say 5 if you're type 1 and you get outcome 1. Let's say 2 if you are type 1 and outcome 2. And 1 if you're type 1 and the outcome is 3. And for the second type, this could be something like 4 and 6 and 3. And for type 3 is going to be 1, 0, and 7. So I just came up with those numbers just from the top of my head. So not necessarily like a good example with the numbers, but let's see. The question for the whole setting is it possible to choose prices? Let's call them P of Ti or P of T, such that the agent would not behave strategically. To complete this definition, to complete the setting, we need to understand like how does the agent makes a decision, and the agent makes a decision according to the quasi-linear utility. So this is why the title of the paper contains this quasi-linear utility, And this just means, so the agent chooses the TJ in such a way to maximize this, thing. So we can say that the utility function is quasi-linear. It's just because there's simple relationship that the value that the agent gets and the number of coins is, and then the payment is just subtracted from here. And the agent wants to maximize this. So he chooses to maximize over all possible TJs, which belongs to the whole set of this possible types in this game. And this is his utility of his own type. So let's actually take a look at what exactly is the cyclic monotonicity condition says. So this says that for any cycle starting at any T1 and going all the way to Tn and going from then the Tn plus 1 is going to cycle back to T1, we have the sum of those differences less or equals than 0. So this is if the mechanism is rationalizable, then we have this. And let's just make a notation that we're going to call the Wij going from I to j. This is going to be V of Tj and X of Ti minus V of Ti and Xi. So this is going to be our definition of the weight in a graph. And remember our running example, the set of types is a discrete set of types. So we have 3 different types. For every pair of nodes in this graph, we have the weight of traveling from I to j according to this definition. The weight going from 1 to 2 is going to be V12. And then there is another weight going from 2 to 1. And this is going to be V21. And note that they're not the same. All other pairs, they also have the way to travel from one to another with this W going from 1 to 3 and W going from 3 to 1, and accordingly going from 2 to 3 and going back. And also there are trivial cycles. The trivial cycle is just going from 2 directly back to 2. Well, the W of 2 and 2 is just from this definition is going to be 0. Same goes for W of 3, 3. The cyclic monotonicity condition here is saying that for any cycle, the sum of the weights along the cycle should not be larger than 0. So in other words, this is saying that there should be no positive cycles in this graph. Let's take a look at those like possible cycles. Like maybe we can travel here from 1 to 2, then from 2 to 3, like this, from 3 to 1. Well, this is one potential cycle, but there are many, many more. So another cycle here. There's this cycle going in triangle, and there's this cycle here, this cycle here, going like this, and there are also these trivial cycles. And also visiting many nodes many times would work. What we see this condition is saying, and this is the most like important context, is if X T P of T truthful, then there are no positive cycles in this graph. And this is a necessary condition. So the cyclic monotonicity is actually a statement about this graph not containing any positive cycles. And when the mechanism is truthful, we get that this property holds. Let's continue and look at the sufficient condition. Well, in fact, what we are going to prove is that cyclic monotonicity is sufficient for X of T to be rationalizable. And then we will see the recipe for computing prices. now we assume that this cyclic monotonicity condition holds, and this means that there are no positive cycles in a graph. Consider some reference point and consider all possible ways to get to some t. This is going to be our t. Using the edges in this graph. And remember the definition of the edges in this graph? Well, there are many ways to travel there, right? We can go here, then here, then here. So consider all possible ways to get from T1 to T. Let's call that, surprisingly, this is going to be called U of T. So this is the supremum over all paths from T0 to T, well, Tn plus 1 equals to this, just the sum over I, starting from 0 and going all the way to n of v, I plus 1, and I. So we consider all possible paths to get there. Well, we can see that since there are no positive cycles in this graph, there is no reason to visit any of the vertex more than once, because visiting a vertex twice means that we traveled around some cycle, and there is no gain for traveling around the cycles. This is because we assumed that this is our now main assumption is that the cyclic monotonicity holds. There are no positive cycles here. So every vertex of the graph on the highest, on the largest path or largest weight path to our destination is going to be visited at most once. And assuming that all those V's, all those weights are finite, and in any finite cycle, this path is going to visit only a finite number of vertices. It's not going to try to cycle infinite many times to gain some advantage. So it's just going to travel to the t, and this is going to have a finite value. So this is maybe the most like tricky part of this argument. This is finite. It has a well-defined meaning. We are going to use this thing to define the payments, and this is like almost trivial because now we are saying that p of ti is going to be the value that ti gets by submitting ti minus this u of t. And we need to prove that those payments, they would render the whole thing truthful. One remark here is the prices, the payments, the p of t will be up to a constant. So this recipe contains a free constant, which doesn't really affect this idea that the agents would be preferring to be truthful, and then there will be a way to normalize those prices. Like, for example, shifting them in the way that the mechanism never actually pays to the agent. So all of those payments will be positive. To prove this, we need to take a look at this following situation. Consider some starting point I and some destination point j, and consider this path to be the optimal path from I to j. So this one is optimal, and we are going to call it u of tj. And consider a different path that goes from I to some alternative k in again in an optimal way, and then it goes directly from k to j. We have that by our definition. This path is the path of the largest weight. So this u of tj is going to be larger or equals than what? Going to tk, right? And then going from k to j. This is going to be u of tj greater or equals than u of tk, and plus v of tj x of tk minus v of tk x of tk. So again, this inequality here is by definition, because traveling from I to j in an optimal way, the largest weight path, choosing the largest weight path is no worse than going optimally to k and then going directly from k to j. And what I did here is I expanded this definition of the weight. So now let's use our definition of the prices here. So from here, we can use this to put here and this to put here. So let's do that. So from here, we actually see that v of tj and x of tj minus p of tj is greater or equals than v of tj and x of tk minus p of tk. And this holds for any tj and tk. And this is exactly what it means for the mechanism to be truthful. So what we've got here is that we assumed the cyclic monotonicity condition. Then we decided to choose our price according to this. And we had this u of t as the weight of the largest path traveling from some reference point to the point t. And because there are, by assumption, by cyclic monotonicity condition, there are no positive cycles here, we got that this thing is finite. And then from there, we got that this is actually the payment that that gets us what we wanted.